Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, I'm going to build a reservoir and use the outflow curve reservoir method. We're going to start from scratch. As you can see, I have nothing loaded into my HMS program. And once we get a few things loaded up, the objective is going to be what is the minimum infiltration rate in the subbasin that will keep the reservoir pool elevation at most 1455 feet? So obviously we need more information to actually answer that question, but we'll return to that question to focus in once we get some stuff built. All right, well, starting from scratch, we got a lot to do. Let's get started. I'll go ahead and create a project. Go ahead and give the project a name. I'm going to call my project exercise 8 and then navigate to the directory you want that project to be saved to. Okay. And then I'm going to be using US customary units. So go ahead and click create. The project's created. Next, I want to create a basin. So we'll go up to components and then basin model manager, new. I'm just going to use the default name for the basin and for a number of the other elements that I create. So basin 1 is fine for me. I'll go ahead and click create. Here is my basin. I'm going to expand that and then click on basin 1 so I can see the basin model map here in this panel. Next, I need to build out my meteorologic elements, my hydrology network. So let's start with a subbasin, and that's going to just be right there. I'll just assume these default names are fine, subbasin 1. After that, downstream of the subbasin, I want to put a reservoir. So I'll put that right there. We'll call it reservoir 1. After that, I want a reach. So I'll click the reach tool right here, single left click on the upstream end of the reach, and then another single left click on the downstream end of the reach, and then click create. And then lastly, let's end with a sink that'll be downstream of the reach. So these are just elements I'm sketching out onto the map. I'm not importing a terrain file and delineating a watershed. None of these elements here have a coordinate system, and that's fine. The theme of this lesson will be to sort of keep things simple since we're starting from scratch and there's just a ton of things to do. All right, let's go ahead and connect these elements so we have a connected network. I like to do this from upstream to the downstream direction. So starting with subbase, I'm going to go ahead and right click, connect downstream, and then do a single left click on the reservoir because that'll be our next downstream element. At any time, we can just kind of pick them up and move them around if we want the location to be a little different. With reservoir, now we need to connect that to the reach. So I'll go right click, connect downstream, and then single left click on the reach. And then finally, right click on the reach, connect downstream, and then click on the sink. All right, so our network is now connected. That looks good. Next, what we want to do is actually define the parameters of these hydrologic elements. So we'll start with the subbasin. When I click on the subbasin here in the model map, or I could do the same thing up here in the Watershed Explorer, I now have the basin elements down here in the components editor. All right, well, I'm going to start with, first of all, putting the required area. I'll say it's 80 miles squared. And then down here at the bottom, I'm going to go with a loss method of initial and constant. That works fine. Transform method, I'm going to go with Clark unit hydrograph. So just using the default values, at least what I have saved as default. And then for base flow method, I'm actually going to just keep it simple and say no base flow. And then go ahead and click save. The next tab over after subbasin here in the components editor is the loss tab. This is where I need to provide the loss parameters, which I'm going to go with 0.20 for the initial loss in inches, 0.30, which is the constant infiltration rate, and then the percent impervious is going to be 10%. This constant infiltration rate will be the decision variable that we change later on when we start running simulations and trying to keep that pool elevation of the reservoir down below 1455. For now, I'm just going to save it and we'll just start with 0.3 inches per hour as our first trial run, but that's still a long ways off. After the last tab, I have to define the transform method parameters. Keep in mind from the subbasin tab, we're using the Clark unit hydrograph. So the parameters on this transform tab are dependent on that selected method. What I'm going to use for method is just standard, so we'll keep that there. Time of concentration is going to be 3 hours, and then storage coefficient will be 1 hour. Then I'll go ahead and click save. We also have to define the parameters for our reservoir and the reach. I'm going to go ahead and do the reach right now because I just think that's quick and simple. The routing method we're going to use is lag and K. So, and then for the loss and gain method, I'm just going to leave it at none. So I'm going to go ahead and click save. And then over in the routing tab, I now need to define that lag constant and the K constant. I'm going to use a constant lag and a constant K. So the lag is going to be 1 hour, and then the constant K parameter is going to be 0.25 hours or 15 minutes. And then go ahead and click Save. Last, we'll click on the reservoir and define the parameters here. The title of this exercise is Reservoir Using Outflow Curve. So the method we'll use for our reservoir here is Outflow Curve. There's no gates, there's no control structures or logic involved with reservoir release. It simply acts as a detention pond, basically an unmanned broad crested weir that's dependent on the inflow, the reservoir geometry, and the geometry of the weir or the spillway. So it's just treat it like a spillway. All right, next down is the storage method. I'm going to select elevation storage discharge. After that, I need to provide the storage discharge function, the storage elevation function, and then the initial conditions of the reservoir. So as you see, the first two are paired data sets. And right now I don't have any paired data sets saved in the project because we just created the project and we haven't done that yet. So what we're going to do is come up here to components and then click on paired data manager. The first one we want to define is storage discharge function. That's the first one here for data type. Go ahead and click new, and then I'll paste in the name and then create. All right, the other type of paired data set that we need to provide is elevation storage. And then I'll go ahead and click new. I'll give it a name, elevation storage reservoir 1, and create. Okay, so now up here in the Watershed Explorer, I have a directory for paired data. And if I expand that, I have my two data sets. There's the storage discharge for reservoir 1 and elevation storage for reservoir 1. Let's start with the elevation storage first. So when I click on this down here in the components editor, I can select either manual entry or DSS. Manual entry would just involve typing or pasting in the values in a table here and confirming in a graph. But then DSS is what I actually want to do in this exercise because it's different and it's good to know how to do this. DSS files are more portable. You can very quickly copy them, the paths to different DSS files and so on. And it's just, it's a good thing to know. So let's go ahead and do that. The default DSS file path name here shows the name of the project and then the name of the project.dss. This is the DSS file I'm going to navigate to create a paired data set, which I will later assign to this elevation storage curve. All right, I have DSSVue up on screen here. I'm going to go ahead and open that DSS file that's associated with the project. So here's the project, and then exercise.8.dss is the file. It says there's no records. That's what I expected to see. And now what we want to do is create a paired data set to represent that elevation storage. This is basically the geometry of our reservoir. So we're going to go up to data entry, manual paired data. Now I'm going to go through a few steps that aren't covered in the HMS lessons, but what's happening here is covered in the HEC DSSVue lessons I've provided. So go ahead and check out the description of this video. I'll leave a link to a DSSVue lesson that describes creating a paired data set. All right. Well, anyway, what we need to know is just follow along here. I'm going to go ahead for part C and call it elevation storage. So as I tab to the next path name part, the path name will start getting built down here. This is really all I need is part C to know what it is. I don't need to define the project or the element. I mean, I can do that, but I think this is sufficient since I'm only going to have one paired data set representing elevation and storage for this project. Up in part C here, the first value is x, the independent variable, and the second value is y, the dependent variable. So when we come down here to units of x, this is what is the unit of elevation. I'm just going to go ahead and type in feet. Now I tried this before and had a problem when I typed out FEET, but I got it to work when I just typed in FT. Now I'm not sure if that was because I had another problem going on, but I'm just going to go with FT. And then the type will be linear for the axes, and then the units for the storage is going to be acre feet, and then the type for the y-axis will also be linear. Down here in the table, now I need to paste in the actual data for that elevation storage. What I've done in preparation for this lesson is created a geometry for the reservoir where the base of the reservoir will be at 1,350 feet, and then the top of the reservoir will be here at 1,500 feet. So this first column is elevation, And as the elevation increases, the area will also increase. And from those values, we can calculate what that storage would be. I also decided that the invert of the spillway is going to be at 1,450 feet right here. So that represents a height of 0. And of course, every elevation below that would also have a height of 0. However, once we go up 10 feet of elevation, that would represent 10 feet height above the spillway invert. 1470 is 20 feet above 1450, and that's where I get the 20 from over here. And then knowing that the flow rate over a weir, a broad crested weir, or most weirs, is a function of the height, h here, to the 1.5 power. I just made up some numbers here for discharge. So we have discharge values corresponding to the different heights and also elevations. All right, with all that said, now I have the information I need for the paired data set. I'm going to go ahead and minimize that. What we're working with here is elevation versus storage. So if I go back to my Excel, I need the elevation column and the storage column right here. So I'm going to go ahead and just copy onto my clipboard with Control C. And then over here, I'm going to navigate to this first record and then click the paste button. And then the values popped into place right there. So I'm going to go ahead and click save. No, I don't need to revisit that. Select the record and then look at the plot. So this is what I expected to see, where I have elevation increasing from the base of 1350 all the way to 1500, and then the storage increasing as well. I'm going to do the same thing for the storage discharge curve. So I'll go up to data entry, manual paired data. This is going to be storage. And I was going to type discharge, but I also want to keep sensitive and keep consistent with the Part C requirements that HMS identifies in their directory. This is the page I was thinking about. We have Part C descriptors for DSS paths, where we have air pressure, albedo, aquifer, and there isn't one for storage discharge, but there is one for storage flow. So let me just do a search for storage and then try to find it. That's elevation storage. That's storage by itself. Storage flow right here. Okay, so storage flow is a manually entered storage discharge function defined in the paired data manager. So I'm going to use the term flow for part C in the Y variable instead of discharge. And then I'll just paste the flow in right there. All right, as before, I don't think I need to be any more descriptive for my path name since I only have one paired data set for storage discharge. But what I do need to do is enter the units again. So for storage, this is going to be acre feet. And then for the flow, that's going to be in CFS. Again, the axes will be linear. And now I just need to paste in my data here. So storage is going to be this column here. And then the discharge is going to be this column over here. So I've actually made a copy of that. So here is the storage discharge values. I'm just going to Control C to copy. And then I think I can just right click and paste. Yeah, so same thing. You can use the paste button here or right click paste. I believe Control V will also paste. All right, let's go ahead and hit save and then take a peek at that data right here. As the storage increases, the discharge does as well. All right, so we got what we need to do in DSS for now. Okay, back in HMS, we can now make those assignments. So if I click on the storage discharge paired data set here under paired data, I can now select DSS. And now I want to navigate to the DSS file that I was just making edits in that's associated with this project. So I'll click on the folder icon and then navigate to my exercise DSS file, click select. Now when I click this report icon, I see the two paths that I just created in DSSVue. So right now we're working with storage discharge, which is storage flow. And then I'll click this set path name button, and that will populate the DSS path name over here in the components editor. So I click that, close the dialog box. Here's the storage flow, which is all I have for my path name. Now I'm going to go ahead and click save. Now, one thing I noticed when preparing this lesson is when I click save, it's actually going to add a few more things to my path name. There's save, and now it's saved, but it also added the word table for part F and storage discharge reservoir 1 for part B, it looks like. I'm not a big fan of that. And what I think HMS wants to tell me is that we need to have something in parts B and F for this to work. So what I'm going to do is go back to DSSVue. And then for both of these paired data sets, I'm going to rename them and just type in something simple, short, and generic for parts B and F to satisfy that HMS requirement. So I'll click rename. And then for part B, I'll just say reservoir 1. Part F, I'll also say reservoir 1. As soon as I tab off, the full path name updates based on the parts that I entered. So that looks good right there. I'll go ahead and click OK. It's been renamed, and now we see the reservoir 1 in the parts B and F. Same thing, I'll go ahead and click rename, paste in part B, paste in part F, just reservoir 1. OK. Okay. All right, so that's been saved. Let's go back to this step right here. We still have the correct file selected. Now I'm going to select those path names again. So this is storage flow, set path name. Now if I save it, I believe it won't change. Good. Yeah, so it didn't change there. Let's do the same thing with elevation storage to select the path. This one right here, click set path name and then save. Okay, I'm confident that that worked. Now we can go ahead back to our reservoir element right here and then make those selections. So we'll assign storage discharge to storage discharge, storage elevation to storage elevation. All right, the last parameter here for the reservoir is the initial conditions. The default value is inflow equals outflow. What I want to do is start the reservoir right at the invert, which is an elevation of 1450. So I'm going to select elevation, type in 1450, and hit save. All right, that's all we need to do right now for the basin model. Before we can run a simulation, we need to create the other two required parts, which is a meteorologic model and a control specification. We can create both of those from the components editor. And let's actually start with the control specification first because it's quick and simple. So I'll go ahead and click Control Specification Manager, and then I'll go ahead and click New. I'll use the name Control 1, that works fine, and then close that. Here is our Control 1 control specification, and all we need to do is define the start and end date time and time interval of the simulation. So I'll go ahead and use this right here. It's going to be for the first 3 days of March 2024. I'm going to start it at midnight, so that's why I'm saying March 4th. It just goes all the way through March 3rd. And then I'll leave the time interval here at 15 minutes. All right, so that was it for controlled specification. The last part that we need to add before creating a simulation run is creating a meteorologic model. So I'll open up the MMM, click New, and then say Create for MET1. That's a fine name. Then here is my Meteorologic model. Down here in the Components editor, we see the default values here. And I'm just going to go with the default values, which is precipitation method is a specified hyetograph. And clearly there's a lot of other options, but this is probably one of the quicker, simpler methods to use for precipitation. Also, I'm going to leave all the other methods to none to, again, sort of keep things simple. If I click on the icon here, specified hyetograph, I now need to identify which subbasin has which time series gauge data for my hyetograph. Before I can do that, I need to associate the meteorologic model with a basin so it can display all the subbasins in this tab. So I'll go back up to the meteorologic model, click on the basins tab, and then for basin 1 here, our one and only basin, we will go ahead and change no to yes. And then I'm going to go ahead and click save. And now click on specified hyetograph again. And now we have our subbasin 1 that's listed in this table. Right now, we don't have any other gauge data, but what it's looking for is precipitation time series gauge data, which would be associated with this subbasin 1 when we run the simulation. So to do that, we'll go up to the Components menu and then Time Series Data Manager. For data type, I'm going to select Precipitation Gauges, so that's the first one here, and then click New. For the name, I'm going to call it Precipitation Sub 1, and then Create. We can close that. Now I have a new directory up here in my Watershed Explorer for time series data. So I'll expand the precipitation gauges directory. And right here, precipitation sub 1 is my time series data set. Down here in the components editor, we need to provide the data. And just as before, I'm going to go with the DSS record where we need to provide the file name and the path name. Back to DSSVue, we need to provide not a paired data set, but a time series data set. So I'll go ahead and click that. Here is the data. It looks a lot like the paired data set, but one difference is we have time data down here with only one value as opposed to an XY paired data set. As before, I assume I'm going to have to type in res something for B and also something for F. So I'm just going to go ahead and do that now. For part C, I want to use incremental precipitation. So I'm going to bring up the descriptors one more time and then type in precip and then look for my precipitation incremental. Okay, there it is. precip-inc. So I'm just going to copy that. This is incremental precipitation for a time series gauge or sub-basin element. All right, so that will be my type C here. I'll just paste that in and then tab. So this is my completed path name, which I'm hoping is good enough for HMS to actually save. We shall see. For the start date, I'm going to say March 1st, 2024 at 0 hours. The units will be in inches. The type is actually going to be period cumulative. This is the cumulative rainfall in inches for every 15 minutes. So down here, you can see we start at March 1st at midnight, and then the next time step is 1 o'clock. And that's not what I want. I want 15 minutes. So that's where part E comes into play. I need to change that to 15 minutes. Okay, good. So now the first step is midnight. The second step is 15 minutes later, and so on. Once I paste the data in here, the other columns for date and time will expand accordingly. All right, back to Excel. I prepared some precipitation data here, starting with, again, midnight on March 1st and extending down for the next 3 days at a 15-minute time interval. Here in column 6 is going to be my data, so I'm just going to go ahead and copy that and then paste it in here. So let me try Control V here. Yep, that worked too. Cool. And then hit save. And no, we don't need to see that, but we will take a look at what that data looks like. Here's a plot of that precipitation data. This is incremental precipitation on a 15-minute time step. So you can see we start on March 1st, and then I'm just kind of scrolling horizontally over to the right. So we have some different storm events over those 3 days. Okay, back to HMS. Now what we can do is select that DSS file right there. And then I'm going to select the precipitation time series data set right here that we just created. That looks good. I'll click set path name. So it's ready to be saved. Let me go ahead and just expand so I can see the whole thing and make sure it doesn't change when I click the save button. Okay, that looked good. And I also noticed that the units changed to incremental inches, which is read from the path that we created. That's good. The time interval is 15 minutes. That was correct before, and it stays 15 minutes. All right. The latitude, longitude, that's not necessary. We're not georeferencing any of our elements here, and we're not using a precipitation method that includes interpolation or inverse distance or anything. So we can leave some of these latitude, longitude properties incomplete. I'll go ahead and click save. Now we're ready to create our simulation run. So I'll go up to Compute, Simulation Run Manager. I'm going to go ahead and say New. This is the 4-step wizard that walks us through the different steps. I'm just going to go ahead and keep it at run 1. That's fine. I was thinking about doing multiple runs and changing the basin so that we could change the actual infiltration rate with different runs, but I'm going to do that a different way, and you'll see. So I'm just going to go ahead and say, yes, we'll call it run 1. We'll use the one and only basin that we've created. We'll use the one and only meteorologic model that we've created, and we'll use the one and only control specification. So I clicked finish, and now we have a run 1 to select right here. And I think we're ready to run. So let's just run it and see what happens. Okay, there's an error. No hyetograph gauge is set for subbasin 1. That's right, I forgot to do that. What I need to do is click on hyetograph, specified hyetograph method, and then for subbasin 1, select that precipitation time series data set that we generated. All right, I think that's the only thing that needs to happen. Let's go ahead and run it again and see what happens. So run. Okay, it finished. Before we look at the actual data and start addressing that question that I started with, let's just go ahead and poke around and look at some results. So this is the graph out of the subbasin. We see on top is the hyetograph. That's the total rainfall in blue, the total precipitation. And then we have the losses in red. And then what isn't lost, that extra blue you can see here, would be the excess precipitation that contributes to the runoff. This in blue here down below is the hydrograph of flow leaving the subbasin and entering the reservoir. The reservoir is just downstream here, so if I right click and then click on graph, we see a couple different plots. On the top is the water surface elevation and storage as a function of time, those 3 days. So you can see it steadily increases. And then down below, we have the discharge or the release, as well as the inflow. Yeah. So we have the inflow here, which looked a lot like the outflow from the subbasin. And then here in blue, we have the release, the discharge from the reservoir. But up at the top is what I'm most interested in, specifically this pool elevation. If we return to the original question that I posed at the beginning, what is the minimum infiltration rate in the subbasin that will keep the reservoir pool elevation most 1455 feet? Let's go ahead and check that out. So right now it's clearly above 1455 because this is 1456.9. What I'm going to do is right click on the reservoir and then click on summary table. And what we have here is the peak elevation is 1457.5. So what I'm going to do in a results tab is say 1457.5. That's the max elevation. I can keep track of the peak discharge here as well, 708.9. Not necessary, but I was just kind of curious what it would be. What we want to do is increase the infiltration rate so that the max elevation in reservoir 1 stays at 1455 or less, which should probably make sense. So if we had a higher infiltration rate, there's less runoff. A lower infiltration rate, there's more runoff. And the more runoff, then the higher the max elevation and vice versa. So let's go ahead and just try a different number. I'm going to go ahead with 0.4 inches per hour, and then we'll go ahead and see what that max elevation in the reservoir is after we run the same simulations with all the same input data. So we only have to change that infiltration rate. We'll head over to the subbasin and then the loss tab. The infiltration rate started at 0.30. So I'm just going to change that to 0.40. Click save. And now I'm going to go ahead and run again. All right, let's go ahead and check out those results. We don't need to look at the graph again. It's going to look similar to what it was, but the summary table, let's just check it out. Yep, similar to what it was. The summary table is really where we can identify that peak elevation without having to search through it, because the same value would exist in this time series table, but we're going to have hundreds of rows to look through if we did that. Here's the summary table. Now the peak elevation is 1455.2. So it definitely came down, but not quite enough. Let me go ahead and add that to our table, 1455.2. So now what we need to do is increase that infiltration rate. This is the average infiltration rate of that 80 square mile basin, a little bit more for the pervious area, that is. Maybe not realistic. I understand that this exercise is a little bit more academic and purposed to understand how HMS works and DSSVue as well, for that matter. So what we want to do is increase this infiltration rate a little bit more, but I think 0.5 would be too much, just judging by what the max elevation was from 0.3 and 0.4. So maybe something like 0.45 or maybe even less. Let's go ahead with 0.45. And this time what I'm going to do is add a computation point to our map to just demonstrate a different way of how to run a simulation. I could do it at the reservoir or at the sink. It doesn't matter. I'm going to do it at the sink. Right click and then select computation point. That adds a little red dot here next to the sink icon, as well as up in the Watershed Explorer. I can also remove the computation point just as well. And another way to assign the computation point is to do so in the computation point manager, which is in parameters, computation point manager. And what I'm going to do is select elements, and I need to just display all the elements here, sync and select. Okay, so it's selected just as it was when we right click on the icon itself. Next, I need to add parameters. So to do that, I'll click on my computation point, sync one, click on parameters. And then the parameter would be for any of the hydrologically upstream elements, at least as far as to the next computation point, should one exist. So I'll click select here. And then what I want to do is select subbasin 1, and its elements are the constant rate of infiltration. That's the parameter that I'm going to be changing. But there's other parameters I could be changing. Unfortunately, there is no parameter for basin area or percent impervious. So that would be nice if that was there, but it's not. So we're going with the average infiltration rate. So I'll go ahead and click select. It's removed from the parameters list, but where it shows up is, I'll show you in just a moment. If I now right click on sync and then I select calibration aids, I have this dialog box here, which now allows me to change the constant rate of infiltration in inches per hour for subbasin 1. Now, right now it's set at 0.40, and I can use the slider tool or just type in my next value I want to use. And when this checkbox is checked, then as soon as I change the value and tab off the field, it will run a new simulation. So you can see how this is a real quick and easy way to change a lot of different parameters in one single dialog box, as opposed to clicking around up in the Watershed Explorer if there's a bunch of different parameters that we want to be changing. All right, like I said, let's go ahead and change this to 0.45. Let me try the slider, see if this works. It'd be nice if it can snap. Doesn't snap. Okay, I got it to 0.45 anyway. So if I tab off, it should have ran a new simulation. It did, yep, because it's 2:18 right now. That was 10 seconds ago. All right, let's go ahead and check out what 0.45 constant infiltration will do to that max pool elevation in the reservoir. I'm going to go ahead and go right click and hold on a second. There we go. View results from run 1, summary table. 1454.5. So it's actually below our 1455 threshold, but I'm going to type that result in anyway. So we need a number between 0.4 and 0.45. What do you guys think? Anyone's guess? 0.42? Yeah, let's go ahead with 0.42. I'll go ahead and go back to HMS, close that. And now I'm just going to type in 0.42 and then tab, and then it ran. So I'll go right click and then summary table, 1454.9, almost there. All right, I think the answer for us is going to be 0.41. So we'll try that one last, 0.41. And it ran because I hit tab. And then if you don't have this checkbox checked right here, you can just force a run by clicking apply. Right click, and the summary table is, okay, 1455.1. Okay, so I guess we have to dial back to the previous iteration. So this was 1455.1. So what that tells us is that the answer is really between 0.41 and 0.42. But to be safe, we'll just go with 0.42 for our answer, for the minimum infiltration rate of the subbasin to keep that max elevation of the reservoir at most 1455.0 feet. Well, I hope that was helpful. This was the end of our exercise. We answered a question about infiltration rates and basins. We set up a meteorologic model, a basin model, ran the simulation, and even dabbled with some DSS files and paths to link all the data together.